Hi, welcome to the Lab 11 video for Math 215. And as I'm going through this video, I'm going to be referring to the PDF a lot. And so I'd recommend, first of all, read all the way through the PDF because there's a lot of good information hidden in there that's really helpful. And also, if you're watching the video, just be able to follow along in the PDF because I'll be referring to a lot of stuff there. So starting off with problem one, it refers to some weird different terminology that we may not be familiar with yet. It wants you to return the coordinate of the projection with respect to the basis vector u. Now that seems confusing, but if we go just a couple of paragraphs up, we see a sentence. We call this scalar, the scalar being u dot x, at the coordinate of the vector projection with respect to the basis vector u. So that's exactly what we want. And it just so happens that our function gives us a u and x, and so all we need to return is just the dot product of u and x, because that is what our coordinate of the projection with respect to u is. So it seems confusing, but again, all you need to return is just the dot product. Now for number two, and let me just clarify what this is doing. We have this line, let's say, that's dictated by some vector u. That can just be used to explain it. We also have another vector, x, let's say there, and we want to see the projection of x onto u, which if you study other linear algebra, you'll get that. If I'm writing that down correctly, or you'll want to write it the opposite way, and that's u or l, I'll call it u this time. And so you want to figure out that. Obviously, this is a vector, but based on how steep this angle is, u of x, how steep this x angle is, we'll get a shorter or a longer projection. And that's actually almost what the dot product does, because let's say we have our u over here, and we have our x. That dot product will be 0, because the dot product of any two perpendicular vectors is 0. And so, yeah, we'll have a very, very small projection. However, if our u looks like this and our x looks like that, the dot product will be very high, and thus our projection, or the scalar coordinate of our projection, will be very high as well. So that's why it works out. Now for problem two, we're doing a very similar thing, except we're going to do it in 3 dimensions this time, which definitely makes it a little bit trickier. So rather than giving one u, we're given 2 u's, because you always need 2 vectors to determine a plane. u1 and u2. And they want us to find, say we have some vector x that's somewhere into the plane. I can't draw that. But they want us to figure out the projection. And what they suggest doing is your function should be able to handle vectors of any size. And it should, in other words, your function should take the vectors u1 and u2, which you have, build the matrix u as shown in equation 3 above. So yeah, this is where I'll refer to the PDF. If we look at equation 3, we have this u matrix, which is 1 over root 6, 2 over root 6, 1 over root 6, and then negative 1 over root 2, 0, and 1 over root 2. And if we look further in the PDF, our u1 is going to be that row, and our u2 is going to be that row. And so if we want to make this u matrix as described by these 2 vectors, then the notation that I would use is I would say something like this. U equals np dot array. It's always good to have np dot array in front of everything. And remember, np dot array, it's a function, so we need these parentheses. A function means you have parentheses. However, it takes as input a list, so we need to have these brackets to say we have this list. And inside that, we want our first row, we want all of our rows. Now, if you look at our first row, we know that our first row is just u1, and we're given u1 as input, so we can use that. And our second row will be u2. And that's actually all it is. So this will make the list of these 2 rows, and then using the function np.array with these parentheses, we'll get our u matrix. And then builds the u matrix, as in the equation above, and then returns the product ux, which again will always be a matrix multiplication. You'll never do, as far as I know, in Math 215, you'll never do like u times x like that. you always do a matrix multiplication. So then for problem 3, moving on, it wants to complete the covariance matrix of the total data set using equation 4. Another like initially scary thing. But yeah, if we just go up to equation 4 in the PDF, which I think is 1 or 2 pages above, we get this equation, 1 over n minus 1 times x transpose. Again, another matrix multiplication. And they actually give us our x. They say you should use the full data set x total here. So that's what we'll use as x. And that's just transpose. We know how to do that. And because this will be a matrix multiplication, you'll do something like np.mapmul x total, and then np.transpose x total. As for the n, if we look at the example that's given in the PDF, we can see that our x total is this group of x1, x2, x3, x4 vectors. And the example that they do, they have n is 4. So yeah, n will be the amount of vectors in your x total. In other words, the amount of columns. And so what I would do for n right here is I would say the length of x total at 0, because this will notate to you the amount of columns in your x total matrix. And so use that as the n, minus it by 1, do the inverse, and then multiply it by the matrix multiplication of x and x transpose, and that will get you your covariance matrix. Again, save this as the equation to get it rather than the matrix itself. Then for problem 4, it says compute the eigenvalues and eigenvectors. Save the 3 largest eigenvalues and 3 largest eigenvectors. So yeah, they say in the line above that to get those values and vectors, we can do this command, np.lnog.eig of w. And we'll just use w from the problem before. And L will have, yeah, these list of values. And it will already be sorted from largest to smallest. And so to look at the largest, we could just say like L at 0. So hint, that I'm pretty sure is what you'll do for the first one. Let me just make sure. Yep. Second one and third one, you use obviously different indices. Now, a very, very similar thing for your U1. However, you'll use P, and it says that the corresponding eigenvectors are actually the columns in P, not the rows. And so again, if we want to do the columns, we would do this notation, the colon, comma, 0, which means we're going to look at all the rows, and we're going to look at all of the first entries in those rows, which is the first column. And again, you'll change this value depending on what eigenvector you're looking at. Now problem 5 requires a little bit of explanation that I feel like isn't there. But if you do look in the problem summary above it, it should help to give a little bit of hint towards what's going on. And so they want you to figure out the total variance of our original data set. So yeah, if we go to the paragraph right below problem 4, it says if these are denoted as our eigenvectors, or our eigenvalues, excuse me, our L1, L2, then the total variance of the data in the direction of that is measured by that. So if we looked at the total data in the direction of U1, then the variance for that would be just the eigenvalue 1. So when they ask for the total variance of everything, that would be looking at the one spanned by U1, U2, all the way to U100. And so to do that, we can actually just say that the total variance is going to be the sum of all my eigenvectors. You can put NP right there if you want to. So because, or not our eigenvectors, our eigenvalues. And so if we calculate the total of all those eigenvalues, then we'll get the total variance. And then for the part 2 of that, if we want to find the reduced variance, it says it wants to find the data set obtained by projecting the subspace spanned by eigenvectors U1 and U2. So that's just asking for, again, if the variance of the subspace projected onto U1 is lambda 1, then U1 and U2 is just going to be lambda 1 plus lambda 2. So your reduced variance will just be lambda 1 plus lambda 2, or L1 plus L2. Isn't that, it seems complicated, but it's just going to be that simple answer. And then it wants you to figure out the relative variance, which you can just do the reduced variance divided by the total variance. And what they want you to figure out in this is that usually the top eigenvectors or top eigenvalues are the most important. And so even though we're only using 2 of the eigenvalues for our reduced variance, it will be like 99% of the data or something like that. That should help with problem 5. Then for problem 6, project the data in the arrays to the two-dimensional subspace spanned by U1 and U2. And so this is actually when we'll call our function from problem 2, our projection 2D, projection 2D. And if you recall, our projection 2D takes in 3 things. The first two things are our vectors that span the subspace. And so they want us to use U1 and U2, and we save that U1 and U2 in problem 4, so we can use them right here. And then they want us to use different x's that we want to plot on this subspace, project onto the subspace. And so you'll use like xneg, xpos, Alice, or Bob for your respective ones. And that should be pretty easy to tell which one. They're just named differently. And that's actually all you need to do, because this will return the projection, which is what we want. And then problem 7, the last one, comparing the plots of xneg and xpos, make a prediction about the likelihood of Alice or Bob developing this form of cancer. And so if we go over to here and we look at, I'll help interpret this for you guys. If we look at the giant function that they have for problem 7, say z1 is Alice, just for now. Or actually, we want to use our xpos and xneg first. So let's say it's xpos. If we look in that first if loop, that's going to deal with our z1. And that c equals b that you see written there means that the color is going to be blue. So if we say, when we use plot data, we have xpos first, then we know x positive will correlate to the blue color, and z2, I think, if we have it as negative, I'm pretty sure, yeah, the color is red. And so that will be our red color. I'm not sure if they already have it inputted for you, but yeah, just remember that whatever you put as 1 will be blue, and whatever you put as 2 will be red. And so, once again, we want to figure out whether Alice or Bob are positive or negative for this cancer test. And Alice, let's say you put her in Z3, then that will be G, which is green. And so that Alice marker, if you put that as Alice, will be green. Whereas if you do the Bob marker as Z4, it doesn't specify that's colors at 7, but just doing it before, the color will be orange. And so if Alice, for instance, was in the red, was grouped together with the red data set, then we know, or sorry, I have to back up a little bit. If Alex was grouped together with the red data set, which was Z1, no, our red was not Z1. Red was Z2, which let's say we had it as negative, I think. So if Alice, the green marker, was in the middle of the red data set, which we said was part of negative, then Alice would be negative. She would not test positive for cancer, which would be a -1. Whereas if Bob, who's the orange, was in the blue data set, Z1, which was our positive, then he would test positive for cancer, which would be our 1. And so yeah, it's a little tricky, but just remember, depending on what colors are grouped together and depending on which ones you set as Z1, Z2, Z3, and Z4, that will tell you whether they test positive or not. And it looks like that's the end of the lab. Again, this isn't too difficult, but if you have any questions, feel free to email me. Thanks for watching.